In this section, we'll look at the Dynamic Background Extraction tool. I think that this is one of the most wonderful tools in PixInsight. I would credit it more than any other processing tool to improving significantly the image quality of the pictures that I make. So let me show you how it works. It is a favorite of mine, so we will find it in the Process Explorer under the Favorites section. I put it there. And this is one of these dynamic tools, so they are associated with an image. So we click on the image to link the utility with this particular image we'll be interacting with. Now the image that I have being displayed right now is a linear image, so it doesn't look like very much. Generally, this process you're going to apply on linear data. You do this early in your processing steps. There are times perhaps where you can do this on nonlinear images, but in general you want to take care of this in the linear stage. We do need to see, however, where the problems are. So I need to apply the screen transfer function to the image so we can see what's going on. I'm going to do on the keyboard Control-A, so we get a nice screen stretch, and we can see in this case I have a picture of a field of galaxies with two relatively bright ones interacting strongly. Now, I will explain in just a few minutes the mechanics of how you go about using this tool to compensate for variations in what could either be flat field errors, light pollution, other forms of gradients, and unwanted signals in this data. We need to model it and compensate for it. That's what this tool allows us to do. But it does it by first making or creating samples, measurements of our image, and then it can model based on those measurements what the sky, what the background looks like so that it can compensate for it and improve the image quality. I need to explain then a bit about samples, because if you understand all of the parts working dynamic of a single sample, and then when we have a whole bunch of them, you can see how they all work together to do what we want them to do. I'm going to then create a single sample on the picture by clicking. There's a sample. Now samples have certain attributes to them. They have a number. We only have one right now, but when we have many, they will be enumerated. They have a position, so we have an X and Y position for this sample. They also have a size. We can change the size of samples, and that can be nice because a larger area means that you are statistically kind of measuring a larger number of pixels, and that might give you a better result. So for the measurement, so I'm just going to increase the size here and show you that does actually work. I've made now a larger little sample here that it's looking at. Below that, you will see that there is a value. Now this is like a brightness value, if you will. It's a measurement of this particular little sample. It's computed. It's computed from the pixels that it's sampling. And this computation, of course, is the main working element of the main working algorithm of the DBE, the Dynamic Background Extraction tool. So you'll see that although there are three channels here, red, green, blue, and then one has this extra K, well, it's the K. We're only looking at a grayscale image, so it's kind of just the luminance value that it calculates, just the brightness value it calculates for this single sample is this number. That's what it is. Now, whenever you have a sample, this graphical representation of the sample, these are the pixels within this little square right there. This tells you, this graphical representation tells you something about how the sample is being handled. One of the things it shows you is based on the color, or the brightness, if you will, of these pixels. It says if the pixels within the sample are being included or not. And we don't necessarily always want to include all pixels. So let me demonstrate that by showing you something else about samples. You can move them around. So if you put your crosshair right on this little sample, I can move him to wherever I want. And of course, you'll see the graphic over here change. If we put it on a star, or these two stars right here, you'll see that they are black in their color. And that's indicating that these pixels are not being included. in the calculation for what would be the sky or the background values within this sample. And that's exactly what we want. We don't want these values, real signal, to be from an object like a stars or galaxies or nebula or whatever. We don't want that to be part of the calculation of the sample. Otherwise, we may harm those particular real signals. We're trying to only compensate for things that were really not part of the reality of what's going on out there. So you'll notice that the next box down below indicates a weight, and this is giving you some indication of how that calculation is proceeding. You'll notice that in this, as I have it displayed now, in this box, I mean, how many pixels here are black, total number of pixels, and how many are kind of white? Well, there are quite a few black pixels here. So it could be 50-50, but apparently it's a little less than that. The number of pixels that are actually being used to calculate this value are 41%. So the weight here is actually giving us the number of pixels that are being used to calculate this number. If I move this to a little area of more sky-like things, you'll notice that the weight rises because now we have more sky-like values, not stars and things, that are being included. But this value and this calculation is affected by other parameters that I'm going to explain in just a moment that deal with, especially this first one here, the tolerance. That is how we choose to model algorithmically each of these samples. But now that we have, one sample, let's put a few more here. Let's just add a few more samples. I will just click on the screen, and I'm clicking in regions that I know to be just the sky. You'll notice these are fairly dark regions. Those are just sky values in this particular image. Now I could also click on things that I know that are artificial bits of signal that it's not really of interest to me, and it's impinging on. It is making the contrast less than what we would like for this image. Again, we'll go into a little more detail here, but just briefly, you'll notice that these galaxies have some tidal tails and things like that. So obviously, I don't want to sample those things because those are real. And it's very hard to see. It's pretty subtle. But the outer parts of this image are darker than this overall kind of central region, which has a little bit of a brightness to it. And that is probably an over or under correction due to a flat field error. Now I see this kind of feature here as well. This could either be a tidal tail, it could be galactic cirrus, it could be an artifact, but it's not the kind of thing that we can compensate for. So I'm not interested in including this. What I want to click on in an image are all bits that I would like to be equal, because that is what we would expect when we apply our model. We want all of these samples to basically work out to be roughly the same at the end of the day. That means that this bright bit, it's brighter here. I want to be sure to sample that region because I want all of these regions to have that kind of compensated value after it applies this model to the image. So that's the logic of how you click on the screen. You want to be sure to click on everything that you want to be compensated for. That's the idea. Now that I have a lot of samples, I can demonstrate a few more things. You already know we can move them around, but we can also delete them. So if we don't like a sample on the keyboard, I can hit the delete button and it'll delete the sample, and it'll go to another sample, the green marked one, where again I could delete it. There is also the little X over here where you can remove a sample in this way. So this control allows you to cycle through samples. Oh, let's go the other way. So if you look on the screen, it's kind of hard to tell where the green goes next, but I am cycling through samples that are given their number right here. And you can go to the end. You can go to wherever you need to go. I believe you can even type in the sample that you want to go to. So With this, we now have total control over the samples. We can control their size, we can control their position, and we could technically even do one more control that I'll just mention now. It's not something that I use because I want to use the full computational force, if you will, of this routine. But if I wanted to say, this sample right here, it needs to be a particular value and just don't even bother to calculate it, we can apply a fixed value to a sample by changing the value. You'll notice now it's not grayed out, by literally typing here and creating a value to whatever it is that we want it to be. So that I'm not going to do that. We're going to do this in the normal way, but that's what that box does. If you're going to do something advanced and force a particular value at a particular sample, that's how you would go about doing it. Don't worry about where I've put these particular samples in this image. We're going to look at more strategies for placing samples in just a moment. What I'd like to really show you are the most powerful parameters of the DBE utility, which are the tolerance and shadows relaxation parameters. These two are the ones that you'll very likely be adjusting to do the work. The tolerance one we've already kind of discussed. It is the parameter that determines within a given sample how many pixels are being included in the calculation of this value for the sample and how many are not. And so we can control how permissive, how tolerant that is. What I'm going to do is let's move a sample over, I don't know, some stars or a galaxy, or no, let's just do some stars here. Well, there's a galaxy or something. And as it stands right now, with the tolerance being very, very small, we are basically saying anything that doesn't look like the background or very, very dim background sky values, we are not going to include in the calculation of what the background is. And that means that this galaxy is not included, painted black. But if we increase the tolerance, we are going to make more of these black pixels white, because we will be including them in the calculation for this background value at this sample. And let's make the tolerance, I don't know, something like 5. That should be pretty inclusive. Now you'll note that most of those black pixels go away, and even some of the black pixels that were part of the galaxy. What this means is that when we are more tolerant of values within a given sample, we probably need to be more careful about where we place our samples. So the greater the tolerance, the more conservative you become in terms of the placement of the sample. You really want to place it not on stars or not on something that has real signal that we don't want to include in this calculation. One of the nice things is that using our eye-brain combination, we can do better at this than what a computer can do. We can look at an image and place things accordingly in an area which truly looks something like the background so that it'll calculate properly. But being more tolerant does something else as well. For a given sample, notice that, I'll just put this here again, notice that if we make this a small number, we have a weight that is a smaller number as well, because we're not using as many pixels in the sample, and therefore the weight that we give the sample is going to be small. And this is good. It's good in the sense that, of course, if we happen to have stars or something in the sample, the weight goes down, and so it won't kind of contaminate, a single sample won't contaminate the set of all other samples in the image. But as we raise this tolerance, becoming more permissive, of course the weight goes up as well. So another good reason to be sure that if you're going to be more tolerant, you've got to be sure your samples are really on what you consider the background. Now, to demonstrate all of this stuff with the tolerance and the shadows relaxation, doing it on this astronomical image, because it is a unique image, isn't necessarily the most instructive. So let me demonstrate how this works on an image that I made that we can play with. I'm going to cancel this for the moment. And I'm going to open up a gradient, an image that I made that basically is just a gradient image. I did this in Photoshop. It's a very, very, very faint gradient. So just like a normal linear image, we're going to adjust the screen transfer function, brighten this image. I did Control A on the keyboard. And just as we would normally do, run the DBE utility. Click on the image to link them, and then start adding samples. This is the kind of background gradient that we would want to correct in our image. Now, to make these perhaps a little bit bigger, why don't we make our samples really something large? And as I add samples, everything is going well until I start clicking over here to the right, where the samples become red colored. And that is, of course, an indication that those samples are not being used. And if we really thought that those were part of the background, we would need to do something. In this case, raise the tolerance to be sure that those are being included. So let's just look here at a sample like this, which happens to be right on that borderline numerically between what is somewhat included and what is not. If we raise the tolerance just a little bit, just a tiny, tiny little bit, what we're going to do is we're going to make more pixels in this frame for this sample light colored, and fewer pixels will be dark colored because we're being more inclusive. So watch as I hope this kind of shifts a little bit to the right if I do 0.51. And indeed it does, because we're being just a little bit more inclusive. And again, if we continue to raise this, instead of making it 0.5, let's make it 0.7. Press enter. Now this particular sample has become white, and more samples over here have also become included. Not all of them, but more of them. And if I want all of the samples to become included, I can just raise the tolerance here to some much larger value. I need to click again on another sample here so that it updates the display. And now all samples are being included for purposes of making this model. So that is how the tolerance is used for a given set of samples. If they are not all being included because they are painted red, and the red, by the way, is that is actually a choice that you have here. You can change the bad sample color to any color you like, but by default it's colored red. Just adjust that tolerance field in order to manipulate whether you're including particular samples or not. Since we're on the topic of the tolerance, let me just go back to our astronomical image here. Oops. And let's look at another one of those parameters. Let me create some samples here. What you'll also see in the section is a box here that says Unweighted. And I want to, now that we've talked about the tolerance, we can talk a little bit about what that means. If you have a sample and it has, I don't know, excluded pixels in it, I'm going to pick a region here like this because there's a star or a galaxy or something like that. Basically, not all of the pixels are being used to calculate this value, and so the weight is small, or it's a smaller number than it would otherwise be if we just had picked to put the sample on a region of blank sky. So what that means is with a smaller weight, if this is an area that we want to get the full effect of compensation by the model, if it has a low weight, that won't happen. And it'll always have a low weight if we keep the sample right there anyway, because of the nature of the things that are in the region. Maybe the stars, could be nebulosity, whatever it is. So we can override the weights. We can say, hey, I know that there's all this extra stuff there, but whatever pixels that are not in, you think are part of the background, that are not these excluded ones, go ahead and give that value, whatever it is, its full weight for that region. So basically, by clicking the unweighted box, you make all these weights equal to 1. That gives each sample its full effect of whatever is calculated there, regardless of how many pixels are used to go into that calculation. My guess, or maybe said another way, my hope is that this wouldn't in general be a box that you need to worry about. You don't need to worry about that, because if you pick wisely or you have a high enough tolerance, it's very likely that you're going to have high weights anyway. So for example, if I put this in this region of basically sky, now I have a weight of 0.76, and then if I increase the tolerance to some even much larger number, now my weight goes very high. So clicking or unclicking this box wouldn't matter, because the value is now already close to 1 anyway, 100% anyway. So that's just something to think about. It's why you wouldn't need to worry about this unless there is some reason you just know that for a sample or your samples, you need to force it to apply whatever it calculates at the greatest value that you can.